Hey, my name is Evan Wehr, and I am in the Cleveland Clinic Science Internship Program with the Office of Civic Education Initiatives. My school that I will be attending this coming school year is South Range, and I will be a junior. My mentor's name is Dr. Demir Janingro, and my project title is The Blood-Brain Barrier in Neurological Disease. Its location is at the end of all of the brain capillaries, and only 1% of all biomedical materials can freely cross over a normal functioning blood-brain barrier. If a subject or a person has cerebrovascular inflammation, the blood-brain barrier permeability increases. Cerebrovascular inflammation is caused by most neurological diseases, and its location can make in vivo cumbersome, as well as treatment for patients. The DIV, Dynamic In Vitro Blood-Brain Barrier Cartridge, was developed in the Janingro lab, and it has the potential to make in vitro possible, which is more feasible than in vivo. Each cartridge has a different level of strain, and strain is determined by how much the fibers in the ECS are stretched, 0%, 51%, 79%. The capillaries have holes, and stretching makes less holes, yet all holes larger. Forming the study, there were 3 cartridges with 3 different stretches. Okay, there was shown are pictures of the interior and exterior surfaces of each cartridge according to their stretch. It was unknown if these cartridges would replicate the blood-brain barrier's attributes. Astrocyte cells would be run through the lumen regions, and samples would be searched for cells. The cells found would be taken note of. And note, astrocyte cells were used for practicality. It was predicted that if astrocyte cells/media were run through the cartridge's lumen region, the following would happen in each cartridge. In the 0% stretch cartridge, cells would not cross over the ECS. In the 51% stretch cartridge, cells would not cross over to the ECS. And in the 79% stretch cartridge, cells will cross over to the ECS. First, we cleaned the cartridges with sterile water, and then we ran astrocyte media/cells through the lumen region of each cartridge. We took 4 samples from every port and reviewed all of the samples from the ports on the 505 field of a hemocytometer with a microscope. We counted how many cells were in each sample. The hypothesis was proven true for the 0% stretched cartridge and the 79 stretched cartridge, while in the 51% stretched cartridge, it did not hold true. The 51% stretched cartridge allowed 2,500 cells per milliliter to cross over, while the 79 stretched cartridge allowed 90,000 cells per milliliter to cross over. In the 0% stretched cartridge, nothing crossed over. The in vitro testing is possible using the DIV blood-brain barrier cartridge. Expanding research, tubing can be attached to the lumen ports of the cartridge to allow material to be pumped through it for a long duration of time, say 48 hours. There is a TEER transendothelial electrical resistance measurement machine that can be hooked up to the electrodes on the bottom of the cartridge. The endothelial cells produce electrical resistance. The TEER machine can register how much electrical resistance there is. Flow cell can record the data gathered by the TEER machine over a long duration of time. If used with the tubing setup, experiments can be run for long durations of time and data can be collected without taking samples. Recommendations. Run Trifin Blue, a dye, through the cartridge's lumen to see if it will cross over the ECS, which it shouldn't. Also, with a biochemistry analyzer, take a sugar reading from the lumen and the ECS before and after reading the dye. This will be determined the amount of sugar that the cells would use, also known as how hard they're working. Thank you. I would like to thank the following people for this help on this project, and without them, none of this would be possible. The Office of Civic Education Initiatives, Dr. Demir Janingro, PhD, and Mohammed Hussein, MD, and Alex Chen.